So this is one of the topic that we are going to talk to you about, the distinction between first order and second order thermodynamic transition. And the first order thermodynamic transition is example is melting transition. Second order thermodynamic transition is a glass transition temperature. And what do you mean by first order transition? And let me give you an example. So the first order transition means that means this continuous change for the first partial derivatives of G. Okay, so I guess then what do you mean by TG, which is that's a second order transition, is you can kind of relate that into the different meanings. So second order transition, which is a TG, and the second order transition and that means once again this continuous change for the second derivatives of Gibbs free energy. Okay, so then what do you mean by first order, first derivative and second order derivative? And then you can start to look for, you remember let's write down the fundamental equation. So delta G is a VdP minus SdT. So this is a fundamental equation that you learned from the thermodynamics class in your macro PChem or the chemical engineering thermodynamics. So here, therefore, I have a volume which says that round G over round P at constant temperature. Right? So the volume, so first order derivative is G, could be an example is a volume is actually first order derivative with T. So if you were to measure the volume, and you should be able to measure that and this continuous change. So you might recall at the Tm, the volume is this continuous increases, right? So therefore, this is a first order thermodynamic transition. And then if you're looking at the meaning of the second order transition, and this is a second order transition, and then if you do this, something as an example, let's see, round T, round volume under constant pressure. Okay, so this is probably related to what we normally called it as expansion constant. But what you can see here is this is should be, this is second order because of this is the first order, this is second order derivative, and should be discontinuous at temperature is Tg. Okay, so what you can see here now is I will replot this idea into so for example here you have discontinuous changes here. Okay. So one way to look at this picture now, I will try in a different way. So to remember, I used to draw the more continuous volume rise as at Tg. So this is what I've been drawing at the Tg here compared to Tm, and that's what I call the second order. And why is that? Is if you take the derivative of this, right, and that will be this and that, and this slope is more or less the volume change in response to temperature change, let's say keeping the ambient temperature condition. So if I draw round V, round T on the constant pressure, for example, this will be a one low value, and there will be another low value, and there will be a discontinuity here. So this one is now, that's why it is a second order transition. Okay, and if you follow the same idea for doing this, so in here, this derivative is a discontinuous second order transition. So going back, and the figure on the left is a little bit misleading, okay? And I want to correct this. In here, if you're looking at, okay, what about if I take the derivative? Temperature versus P. If you do that, this slope is essentially different slope. So they are like this, okay? But at here, the slope at melting transition is really high, and you will have actually infinitely large. Okay, so that's the one, the better picture than the one that's shown in the textbook, and I wish that the authors fix this one. So at melting temperature, your slope here is a discontinuous, and then typically shown as a pretty sharp transition shown up here. Okay, so that's why it is, this makes the first order transition for this. I also find some pictures from the internet. They essentially saying the same thing here, as you can see. And then you see the Tg, the rubbery versus glassy. This is Tm, they call it melt. It's also, you can call it rubbery. There's nothing wrong with that. But this is a this is a crystalline solid, means that there is a solid, and then still this one on below here is you are expecting to see the crystalline domain with an amorphous rubbery chain. Okay, and this is what I talked about. And then I am going to, next section, I'm going to talk to you about the differential scanning calorimetry and how this idea. So I like to, at the end, I always like to draw this way. Okay, so think about this. This is your volume, and then this is your temperature. Slow rise, glassy polymer, slow expansion, faster expansion when they have a rubbery domain. But if you do it as a semi-crystalline polymers, eventually there's a discontinuous jump, and then there will be much further increase there. So this is, once again, that's a Tg, that's a Tm. And later, the concept of the differential scanning calorimetry, and this is also comes in handy. Okay, so once again, you remember this is a first order derivative for the gives free energy, the volume. So that's its physical significance. And at the same time, if you remember, enthalpy is internal energy times P times V. So this is essentially when there is a discontinuity in the volume, you will see the same discontinuity in the H. So this is, you can say this, they are proportional to enthalpy. Okay, so now all of a sudden that I can change the volume term into something that is related to the enthalpy, and this enthalpy is something that is easier to be measured in the instrument measuring the heat transaction. Okay, and then I'm going to talk to you about in the next section.